Hello and welcome to this course in database engineering. Almost everyone has used a database, and more likely, information about us is probably present in many databases all over the world. But who understands what a database is and how important database engineering is to global industry, government, and organizations? A very straightforward description of a database is that it is a form of electronic storage in which data is held. Of course, that explanation does not even come close to explaining the impact of database technology. To give an idea of databases in a real-world context, let's briefly describe some typical use cases. For example, your bank uses a database to store data for customers, bank accounts, and transactions. A hospital stores patient data, staff data, laboratory data, and more. And an online store retains your profile information along with your shopping history and accounting transactions. Many of these services have access to a diverse range of data. They collect and store other items such as your location, how long you spend on their platform, and friends you connected with, alongside many more facts. Such online services and social media platforms generate enormous amounts of data due to their large user base and constant user activity. And with the Internet of Things, or IoT, many extra devices are now connected to the Internet. These continual streams of data have led to a revolution in database technology to accommodate the volume, variety, and complexity of what has become known as big data. Whatever the source of the data, a database will typically carry out the following actions, all of which a database engineer must be familiar with. Store the data, form connections or relationships between segmented areas of the data, filter the data to show relevant records, search data to return matching records, and have functions to allow the data to be updated, changed, and deleted as required. Don't worry if you don't fully understand all these terms. For now, you're just receiving a brief introduction to databases and data. During the course, you'll explore these concepts in more detail, alongside the many other tasks that form the duties of a database engineer. You'll learn about the concepts of data and databases, how data is related in a database, and different database structures and their uses, how to perform, create, read, update, and delete operations, how to use SQL operators to sort and filter data, what database normalization is, and how to normalize a database. You'll get to build a fully operational database, and you'll also install and set up software called XAMPP on your computer to help progress your local and remote database learning. You're not expected to be a database engineer just now. There are many videos in your course that will gradually guide you toward that goal. Watch, pause, rewind, and rewatch the videos until you are confident in your skills. Then consolidate your knowledge by consulting the course readings, and put your skills into practice during the course exercises. Along the way, you'll encounter several knowledge quizzes where you can self-check your progress, and you're not alone in considering a career as a database engineer, which is why you'll also work with course discussion prompts that enable you to connect with your classmates. It's a great way to share knowledge, discuss difficulties, and make new friends. To be successful in this course, it is helpful to commit to a regular and disciplined approach to learning. You need to be serious about your study, and if possible, map out a study schedule with dates and times that you can devote to attending the course. It's an online, self-paced course, but it does help to think of your study in terms of regular attendance at a learning institute. In summary, this course provides you with a complete introduction to databases, and it's part of a program of courses that lead you toward a career in database engineering.
I really like this idea that in the end, we're all solving human problems through technology. And we're not, as a software engineer, my role is not to simply develop technological solutions. They need to have this human outcome. I'm Daniel Bloomfield-Ramagem. I'm a software engineer for Meta. I joined the company in 2017, and I work out of our Washington, D.C. office. I immediately think of my mother's recipe book, which is a spiral notebook. So she keeps her recipes in a spiral notebook. Every page has a number, and she keeps kind of an index at the beginning of that notebook so she can easily find the recipe. Well, that's a database. So, my mom is a database engineer, perhaps, or not engineer, but certainly she relies and has created her databases. So I like that fun kind of example because it shows the range of things that are possible once you store data in a structured way that can be easily retrieved. And so it's the recipe book, but it's also, the picture I just shared on Facebook that now my friends get to see anywhere they are in the world so quickly. All that is powered by a lot of infrastructure, databases at the core. I think data is at the heart of every application. And so learning to create an effective data layer that can provide the user with quick responses, accurate responses, and results is really critical. And as a database engineer in particular, I think you are involved in such a critical component of building applications, and you have such a large influence in everything else that follows from the data. So that includes the user interface. It includes the clients, the APIs, like all of that gets influenced by how the data layer gets modeled, stored, and all the characteristics of being able to retrieve that data effectively and making it the consumption of that information easy for the rest of the tech stack. So you have a really large influence, and I hope you walk away knowing that you have this very large influence on the development of applications. So technical skills I use on a daily basis. Certainly I code, and when I say code, I mean not only I program using kind of a standard programming languages for web, but I also work in the database space by creating the pipelines that produce, that extract, transform, and load a lot of the data that makes its way into the applications that we develop. The soft skills I use on a daily basis certainly include a lot of communication and organization. It's easy you come out of school and you're so excited about the coding, the technical skills you've learned, and those are obviously very, very important. But I thought code was king. I'm here to program. And I expect people to understand the output of what I'm making. And I learned that is insufficient. And I saw great examples of people who were doing great technically, but they were excelling furthermore on just being able to explain what they were doing, not only to the team internally, but to the people who are going to maybe use those features in the tool set. The perfect is the enemy of the good. Particularly, I think with database development, it's easy to overcomplicate solutions, and especially when you're doing data modeling and data storage. You want to cover every possible variation of data, every different use case, edge case for using that data. And that can lead you down the path of creating very complex data schemas that become hard to maintain, can be not well performant. So you need to iterate on your work. For databases, I would say, try to focus on the here and now needs of data. Be especially mindful of these perceived needs for massive data scalability, which may, again, lead you to overcomplicate your solution when in fact you might need something much smaller scale, at least to kick off and get better understanding of what the feature and the data requirements truly are. So start small, iterate frequently. Write more often. And I know usually when you think of engineers or database programmers, you think the output of your work is, it's the program, it's the code, it's the SQL queries. And yes, it is, but that alone I think is insufficient. So complement that with writing. Now, what are you going to write about? Well, certainly there's documentation that goes along with your code. I have a good colleague at Meta that always tells me when I said I'm done with something, he looks at me and says, "Are you done?" And I said, the first time he said it, I was like, "Yes, I'm done." And he followed up with, is your documentation ready? Is your code checked in the right places? Is the wiki page updated? Did you write a post about this? And so he emphasized the importance of code is the 80%, 20% is that additional communication that's needed. So I would say write more often. Don't be afraid to write imperfectly. Write something, put something out there, whether it's sharing the status of something that you're doing, whether it's just enhancing documentation for something that you're working on. Get into the habit of writing more often. Try to take what you're learning and connect it to something practical that you can see a use for. Whether it's learning about databases and thinking about a recipe book that your mother or father has in a spiral notebook, or maybe baseball cards that you tracked as a child, or comic books that you tracked as a child. Try to think of ways to apply what you're learning technically to these real-life problems. They can be small problems, like finding the recipes at the right time, but they can be, of course, bigger, more perhaps interesting problems around just technical and digital communication between people.
We all use data and databases in our daily online lives. For example, uploading photos to our social media feeds, downloading files at work, and playing games online are all examples of database usage. But what exactly is data, and how does it interact with a database? If you're struggling to answer these questions, don't worry. By the end of this video, you'll be able to describe what a database is at a conceptual level, identify real-world examples of the use of databases, and demonstrate an understanding of how data is organized in a database. So, let's return to the first of our questions. What is data? In basic terms, data is facts and figures about, well, anything. For example, if data were collected on a person, then that data might include their name, age, email, and date of birth. Or the data could be facts and figures related to an online purchase. This could be the order number, description, order quantity and date, and even the customer's email. Data is crucial for individuals as well as organizations. But where is all this data stored? In our digital world, data is no longer stored in manual files. Instead, developers use something called databases. A database is a form of electronic storage in which data is organized systematically. It stores and manipulates data electronically to make it more manageable, efficient, and secure. There are many real-world examples of where databases are used. For example, a bank can use a database to store data for its customers, bank accounts, and transactions. And a hospital uses a database to store patient data, staff data, laboratory data, and much more. At this point, you might be asking yourself, but what does a database actually look like? Well, a database looks like data organized systematically, and this organization typically looks like a spreadsheet or a table. What exactly does the term systematic mean? All data contains elements or features and attributes by which they can be identified. For example, a person can be identified by attributes like their age, height, or hair color, and this data is separated and stored in what's known as entities that represent those elements. As you just learned, an entity is like a table. It contains rows and columns that store data relating to a specific element. In other words, these are relational elements. They're related to one another. These entities could be physical representations, like an employee, a customer, or a product, or they could be conceptual, like an order, an invoice, or quotation. Entities then store data in a table-like format against the attributes or features related to the element. For example, an online store could hold customers' data in a customer entity containing specific attributes relating to the customer. These attributes could include first name, last name, date of birth, and email. And they could also have product data stored in a product entity against attributes like product code, description, price, and availability. In the relational database world, these entities are known as relations or tables. The attributes become the columns of the table, and each table row represents an instance of that entity. As an example, let's take the entities from the online store example that you just explored. These two examples could be combined into a list of orders the store received from its customers. Within a database, this data could be rendered as an order table or entity, and the data could be organized into rows that contain a unique order number, the name of the customer who placed the order, the product that they ordered, and the price of that product. There are many ways to organize data in a database. Relational databases aren't the only kind of databases that you'll encounter. As a database engineer, you'll work with many different types of databases. Here's a few common examples of other types of databases. An object-oriented database is where data is stored in the form of objects instead of tables or relations. An example of this kind of database could be an online bookstore. The store's database could render authors, customers, books, and publishers as classes, like sets or categories. The objects, or instances of these classes, would then hold the actual data. Graph databases store data in the form of nodes. In this case, entities like customers, orders, and products are represented as nodes. The relationships between them are represented as edges. And finally, There's document databases where data is stored as JSON, or JavaScript Object Notation objects. The data is organized into collections like tables. Within each collection are documents written in JSON that record data. So in this example, customer documents are held in a customer collection, while order and product documents are stored in the order and product collections. But where are the databases themselves stored? A database can be hosted on a dedicated machine within the premises of an organization, or it could be hosted on the cloud. Cloud databases are currently a more popular choice. This is because they allow you to store, manage, and retrieve data through a cloud platform, and access data through the internet. And they all provide a lower cost option for data management than other similar options. You should now understand the concept of a database. You should also be able to identify examples of databases and demonstrate how data is organized within a database. Great start. You'll be storing and managing data in no time. Picture yourself in the following scenario. You're managing the database of a large online store. Your database must be able to retrieve a customer's details from one table and then find the order recorded against another table. So how does the database establish a relationship between these pieces of data? Over the next few minutes, you'll explore this process, and by the end of this video, you'll be able to explain why data in a database should be related and identify an instance of related data in a database. Data stored in a database cannot exist in isolation. It must have a relationship with other data so that it can be processed into meaningful information. So how do you make sure that all the data in your database is related? Let's explore how data is related by using the online store as our example. In the database of your online store, you could have an order table and a customer table. To locate the details of a customer's order, you would check the order number against the customer ID. In other words, the database establishes a link between the data and the tables. Let's look at the customer table in more detail. In this table, the columns are customer ID, first name, last name, and email. In relational database terms, these are fields. Then there are several rows which contain data for each of these fields. In relational databases, they are known as records of the table. So, all these fields and rows work together to store information on the customer, also known as the entity. Every row and record in the customer table is an instance of the customer entity. For example, Sarah Hogan, who has a customer ID of C1, is one customer instance. And Katrina Langley, who has a customer ID of C4, is another customer instance. What's most important is that each of these customer instances, or records, must be uniquely identifiable. But what if two or more customers share similar info, like the same first name or last name? To avoid this confusion within the database, you can use a field that contains only unique values like the customer ID. This is called a primary key field. It contains unique values that cannot be replicated elsewhere in the table. So even if two customers share the same name, they'll still have separate customer IDs. This means that your database can determine which customer is the required one. Let's look at the order table next. Just like the customer table, the order table also has fields and records. And in this table, the primary key field is the order ID. But there's also a field named customer ID with the exact same data as the customer data. So what is the purpose of the customer ID in this table? The customer ID is there to help identify who it is that placed the order. So by adding the customer ID field to the order table, a relationship is established between the customer table and the order table. And because of this relationship, you can pull data in a meaningful way from both tables. The customer ID field in the order table is known as the foreign key field. A foreign key is a field in one table that connects to the primary key field in the original table, which in this case is the customer table. So the customer ID is the primary key of the customer table, but it becomes the foreign key in the order table. This way, the relationship is established and the data in these two tables are related. You should now be able to explain the relationships between data in a database and identify instances of related data. Great work. You've probably heard of terms like big data and cloud databases. Maybe you've even encountered them in this course. But do you know what they mean? In this video, You'll discover more about these terms and you'll be able to identify different types of databases and explain how databases have evolved in response to new trends like big data. Databases have been around for a long time and have been influenced by many different trends, but they've undergone a huge change in recent decades. Thanks to the growth of the internet, they now must be able to store ever-increasing amounts of unstructured data. However, this poses difficulties, as they mostly store structured data. Let's briefly look at some of the different types of databases and how they've been affected by this trend. Relational databases have limitations when it comes to storing data because they mostly store structured data. Yet databases are now required to store more and more unstructured data. So the trend in recent years has been to rely on nosql databases instead. NoSQL databases are a type of database that store data in a variety of different formats. Essentially, they provide databases with a flexible structure. This makes scaling easy by facilitating a change to the database structure itself without the need for complex data models. NoSQL databases are used by social media platforms, the Internet of Things, artificial intelligence, and other applications that generate massive amounts of unstructured data. Types of NoSQL databases include document databases, key-value databases, and graph databases. Now that you're familiar with different types of databases, let's take a closer look at big data and cloud databases. Essentially, these terms are used to describe a recent change in our approach to data and databases. Let's start with a look at big data. Big data is complex data that can increase in volume with time. In other words, it's data that can grow exponentially with time. But where does this kind of complex data come from? Social media platforms, online shopping sites, and other services generate massive amounts of data every second of the day as they capture the actions of billions of users around the world. And with the Internet of Things, or IoT, more and more devices are connected to the Internet, generating even more and more data. This is how complex data, or big data, is created. All this data is highly unstructured or semi-structured. Traditional database systems could deal with structured data using tables, records, and relationships. But big data is a whole new challenge. Big data is a combination of structured, semi-structured, and unstructured data collected from many different sources. And it adds more power to data because it can address complex business problems that traditionally structured data can't handle. Finally, big data helps to provide unique insights that can help to improve decision-making, so it's highly valued across many industries. For example, the manufacturing sector processes big data to predict equipment failure by evaluating the current state of machinery, assess production processes by monitoring the production line, respond to customer feedback proactively, and anticipate future demands by monitoring current sales. Retail processes big data to anticipate customer demand, improve customer experience, analyze customer behavior and spending patterns, and identify pricing improvement opportunities. And the telecommunications sector utilizes big data analytics and network usage analytics to plan for infrastructure investments, design new services that meet customer demands, analyze service quality data to predict customer satisfaction, and plan for customer retention mechanisms. Now that you're familiar with big data and how it helps to power businesses, let's move on to another trend in databases: the use of cloud databases. Organizations are moving to the cloud to free themselves from the difficulties of dealing with the infrastructure of physical servers, like maintenance and storage costs. Some examples of cloud storage services include Dropbox and iCloud. With these cloud storage services, it's possible to store documents and other data on the cloud, a much more affordable solution. Another trend in databases is business intelligence, or BI. Traditionally, databases were just a means of storing data. But organizations now utilize their data with business intelligence-related technologies and strategies. With these technologies, organizations can analyze their data and extract valuable information to help them to make informed business decisions. New trends are constantly emerging in database technology, and they'll keep advancing with time. But for now, these are a few of the leading trends that you should be aware of. At this stage in the course, you're probably familiar with the basics of databases and how they store and manage data. But it's also important that you know how to interact with databases in order to work with data. As a data engineer, you can interact with databases using structured query language, or as it's more commonly known, SQL, also pronounced as SQL. Over the next few minutes, you'll learn how to explain what SQL is and outline the role of SQL in databases. So what sort of interactions do database engineers need to establish with databases? Some of the operations you could carry out in the data might require you to create, read, update, and delete data. These operations are also known as CRUD operations. You might already be familiar with some of these operations. If not, don't worry. They'll be covered in depth at later stages in this course. Let's find out more about SQL. SQL is a standard language that can be used with all databases. It's particularly useful when working with relational databases, which require a language that can interact with structured data. Some examples of relational databases that SQL can interact with include mysql, postgresql, Oracle, and Microsoft SQL Server. The next question this raises is, how does a database interpret or read and execute instructions given using SQL? A database interprets and makes sense of SQL instructions with the use of a database management system, or DBMS. As a web developer, you'll execute all SQL instructions on a database using a DBMS. The DBMS takes responsibility for transforming SQL instructions into a form that's understood by the underlying database. This was just a very quick introduction to SQL. At this early stage, you should be able to explain what SQL is and explain the role of SQL in databases. In the upcoming videos, you'll learn more about SQL and develop a deeper understanding of the language. Imagine that you've just been hired to create a database for a college. First, you'd need to create tables to hold data in all aspects of the college. Then you'd need to insert data into these tables, and then modify this data whenever something changes. That's a lot of work, but it's all possible with the use of SQL and CRUD operations. Not familiar with these operations? No problem. Over the next few minutes, you'll learn how to explain the tasks that SQL syntax is used for when building a database, and demonstrate an understanding of the SQL subsets and sublanguages. So, let's return to our college database scenario. How can you possibly make all these changes in the database? Well, with the help of what web developers call CRUD operations. Performing CRUD operations is the most common task when working with a database. CRUD stands for create, read, update, and delete. Or in operational terms, create, add or insert data, read data, update existing data, and delete data. Alongside these operations, there are many other things that SQL can do. Depending on what SQL is used for, it can be divided into many subsections or sublanguages. These include DDL, or Data Definition Language, DML, also known as Data Manipulation Language, DQL, or Data Query Language, and DCL, also called Data Control Language. Let's take a closer look at these languages and their commands, starting with Data Definition Language, or DDL. DDL, as the name says, helps you define data in your database. But what does it mean to define data? Before you can store data in the database, you need to create the database and related objects like tables in which your data will be stored. For this, the DDL part of SQL has a command named create. Then you might need to modify already created database objects. For example, you might need to modify the structure of a table by adding a new column. You can perform this task with the DDL alter command. You can remove an object like a table from a database using the DDL drop command. Data Manipulation Language, or DML commands, are used to manipulate data in the database, like inserting, updating, or deleting data. Most CRUD operations fall under DML. To add data to a table, you can use the insert command. This command lets you specify the fields to add data to, along with the values to be inserted. If you need to edit data that's already inserted into a table, just deploy the update command. And you can specify data to be removed by using the delete command. So far, you've learned how to add database objects and manage data within them. So how do you read or retrieve that data? To read data stored in a database, you can use Data Query Language. DQL defines the select command to be able to retrieve data. Select lets you retrieve data from one or multiple tables, letting you specify the data fields that you want based on preferred filter criteria. And finally, you can also use DCL, or Data Control Language, to control access to the database. For example, using DCL commands, you control access to data stored in the database. Grant and revoke DDL commands are used to give users access privileges to data and to revert access privileges already given to users. You should now be familiar with how SQL acts as the interface between the database and its users, and you should also be able to identify SQL operations and sublanguages. Great work! By now you're most likely familiar with the basics of databases, and you might even have come across some simple SQL syntax. But why do developers use SQL to interact with databases? SQL is a popular language choice for databases because of the many advantages that it offers. Now, over the next few minutes, you'll identify the advantages of SQL and demonstrate how the advantages of SQL assist with database tasks. SQL is the interface or bridge between a relational database and its users and offers web developers a wide range of advantages. Let's look at a few of them. The biggest advantage of SQL is that it requires very little coding skills to use. It's just a set of keywords. There aren't many lines of code required to perform basic CRUD operations, or add, create, update, and delete tasks on the database. So it's a very developer or user-friendly language. SQL's interactivity makes it even more user-friendly because it lets developers write complex queries in a short space of time. So if you need to work with relational databases for your next project, you just need to know what keywords to use and when. SQL is also a standard language that can be used with all relational databases, like MySQL. This also means that there's a lot of support and information available. So, SQL can run on any computer once you have database software installed. SQL is also a portable language. Once you write your code, it can then be used on any hardware and any operating system or platform, wherever you need. So if you write SQL code in a desktop and then move it to a production server environment, it will run the same in both locations. Also, SQL is a comprehensive language that covers all areas of database management and administration. For example, it allows you to create databases, insert, update, and delete data, retrieve and share data among multiple users, and manage database security. This is made possible through subsets of SQL, like DDL, or Data Definition Language, DML, also known as Data Manipulation Language, DQL, or Data Query Language, and DCL, also known as Data Control Language. And the final advantage of SQL is that it lets database users process large amounts of data quickly and efficiently. You now know that SQL is a simple, standard, portable, comprehensive, and efficient language that can be used to communicate and work with relational databases. You're well on your way to mastering SQL. Well done. At this stage of the course, you're probably familiar with the basics of how databases store and interact with data. But how do they store all this data and present it in a logical way? In the form of tables. By the end of this video, you'll be able to outline what a database table is at a conceptual level and explain how data is structured in a database table. As you probably already know, the table is made up of rows and columns which hold data, and a table is stored in a database. In a database that holds multiple tables, these tables are known as relations, as they all relate to one another. In a more conceptual or logical sense, a table is also known as an entity. And in object-oriented databases, or OODB, an entity is an object that has attributes that are like columns or fields in a table. So in essence, a table, entity, and object all refer to the same concept. Within every table are columns, also sometimes called fields or attributes. Each column or field has a unique name and data type. For example, I have a table that contains data on employees in a company. The table organizes the data into columns such as ID and role, and each column can hold different types of data, like numeric or string. A set of columns or fields form a row. In relational database terminology, a row is known as a record. So a record is a combination of columns or fields that contain data. In my employee table, for example, each row is a single employee record. Let's return to columns for a moment. As you now know, every column has a data type. The data type of a column defines what type of value a column can hold, like integer, character, date and time, and so on. It's up to the developer to decide the data type for each column. And it's also a guideline for SQL around what data type to expect in each column, and how to interact with the underlying data stored physically. However, data types can vary depending on the database system. For example, you might have different types for MySQL, SQL Server, or Access. Always refer to the documentation of the relevant database system to check what data types it supports. Generally, all database systems support string data types for storing characters in strings of characters, numeric data types to store exact or whole numbers and approximate numbers, date and time data types to store information on date and time, and binary data types to store images, files, and other information. Another important concept related to tables is domains. A domain is the set of legal values that can be assigned to an attribute. Basically, this means making sure that the values a field can hold are well defined. For example, you can only place numbers in a numerical domain, and you can only place characters or strings of characters in a string domain. And each of these domains must include length, values, and other relevant rules that define its function. Each row or record in a table is also uniquely identified by what's known as a primary key. A column in the table that has unique values will become the primary key of the table. In the employee table, for example, the ID column is the primary key as each ID is unique. This is because the other columns could contain repeating values. For example, two employees may share the same name or role. It's also possible for a primary key to be a combination of columns if a single column alone doesn't possess unique values. You should now be familiar with what a database is and be able to explain how it is structured. You should also be able to explain key concepts such as columns, rows, and keys. Great work. At this stage of the course, you're probably familiar with the relational database model. But to fully understand how a relational database model works, you first need to understand how tables within a database are related. Essentially, relationships are established between tables with the use of keys. By the end of this video, you'll be able to identify the main keys used in tables in a relational database and explain the relationship between keys in a table. The relational database model is based on two main concepts: entities, which are defined as tables, and relations that connect to related tables. To realize how this model works, you need to understand the different key attributes that exist in the relational database. To demonstrate, let's use the example of a sports competition that uses three tables to keep track of the league: the league table, the teams table, and the points table. Each table has relevant columns, where each column represents an attribute of the table entity. The league table keeps track of each team's position in the league, their name, and the state they represent. The team's table tracks the team name, the team captain, and the team coach, and the points table records the team's position in the league, the team's name, and how many points the team has this season. Notice that the teams table includes team name, which also belongs to the league table. These attributes could be of a simple attribute type that can hold a single value. For example, in a table of staff members in a college, each staff name attribute has a single value in each row. Or they could also have a multi-value attribute that can have multiple values, like a list of subjects taught. However, multi-value attributes should be avoided in relational database design. You'll learn more about this concept later in the course. Let's use the example of the staff table to explore some examples of attribute keys. Let's begin with the key attribute. This is a value used to uniquely identify an individual record of data in a table. For example, in the staff table, the key attribute is staff ID. This attribute has unique value in each row of the table, so it's the perfect way to uniquely identify each record of data. In a relational database, there are a range of different types of key attributes. There's also the candidate key attribute. This is any attribute that contains a unique value in each row of the table. In the case of the staff table, both the staff ID and contact numbers are examples of candidate keys. Each has a new unique value in each row. The other columns can contain repeated information, so they're designated as non-key attributes. A composite key is a key that is composed of two or more attributes to form a unique value in each new row. In the staff table, an example of a composite key is a combination of the staff name and staff title, assuming that there isn't another instance of the same combination elsewhere in the table. A composite key is usually considered when a single attribute key can't be identified. A relational database must also contain a primary key. which you should already be familiar with. In the staff table, the staff ID is the primary key. An alternate key, also known as a secondary key, is a candidate key that was not selected to be the primary key. Just like a primary key, it's a column that contains a unique value in each field. For the staff table, the contact number is the secondary key on each row. And finally, there's the foreign key. The foreign key is an attribute in a table that references a unique key in another table. Typically, a foreign key references the primary key of another table. For example, the staff ID might also be a foreign key in one or more tables within a college database. The relationship between primary and foreign keys will be discussed in more detail at a later point in this course. You're now familiar with the different types of keys in a relational database.